Hey guys, welcome back. Let's talk all about residual analysis. What are residuals? Hopefully you have a good sense as to what residuals are, as we've been touching on it thus far. We're talking about it now in the context of variance, and as always, but it's important to recall that residuals are these gray points added up, right? So it's the vertical distance between the line of best fit and each observation. So the dots here are your data points, the gray lines are the residuals, so it's in essence the unexplained variance, right? So when we're talking about variance, this totals the unexplained variance in our model, because here's our line of best fit through the data points, and here is where it's not really fitting very well. And so what are some assumptions about residuals? Recall, residuals are the difference between the predicted and observed scores. That's all this is, right? So here's our observed scores in these dots here, and this is our predicted score on the red line. And so the difference between them when you total them all up is our residuals. And they can be positive or negative. And so when we're quantifying the residuals or looking at the distribution of residuals, really on average they should equal 0, right? Because error is random, and therefore residuals should be normally distributed around 0. And so this is from an example that we've used previously, but what I've done differently here is I've actually taken each of the residuals from the data point. So here it'd be a small amount, large amount. I mean, this isn't actually the figure for the data, but it conceptually is the same thing. So I've taken all of the numbers from the distance of these residuals from the line, and I've plotted it. And you see it's normally distributed, right? And this is what you're looking for when we're talking about the assumptions, right? So if we flick back super quickly to our assumptions, and we're talking about the assumptions of normality. Again, many people relate this assumption to the variables, which is true. We want our variables to be normally distributed, but in some case, the model can allow for the variable to be slightly skewed. What's really important is that your residuals are normally distributed. Why does it get conflated with when we talk about the variables versus the residuals? Well, often at times, if you look at your residuals here, and if they're highly skewed, and then you look at your individual variables in your model and you see one is highly skewed, oftentimes if you can address that individual variable, it'll fix the residuals. So that's why they can be conflated. But really, the main focus for the assumption is that your residuals are normally distributed and they should be around 0, because error is random. And so how do we diagnose this? How do we assess this assumption as to whether the residuals are normally distributed? Well, we use a normal probability plot, which is called a QQ plot. And the residuals are normally distributed if the points cluster along the diagonal. So here we have our diagonal here. And if they're normally distributed, the points should all cluster along the diagram. These can be difficult to read when you're first looking at them. You may ask yourself, like, how stringent should you be? Look here at the ends, they seem to be deviating quite a lot from the line, and over here. Really, the ruling guide of thumb, I think that helps, is when you're looking at a QQ plot, start with the middle. And really, this is typical of what you should be seeing with a really nice, normally distributed data residuals that you have here. So we're fitting the model against standardized residuals in the QQ plot, and you see here that they're all really closely fitting onto the line. So that indicates to me that, yeah, in fact, the residuals are normally distributed, and it maps onto what we're sort of seeing in the data as well. And so it's to be expected to have deviations at the edge of this plot. So don't let that change your interpretation. Focus a lot more on the center of where a lot of the data points are there. And then we have another test, of course, which is the we can look at the predicted values versus the residuals, but in Jamovi this is called fitted values versus residuals. And so you can create this scatter plot, and you expect there won't be any clear patterns in the spread of points. What you're really looking for here is like a diffuse cloud of data points, so that you can't see any pattern. It looks like a scattergun, or you're looking at the dots and you don't see any observable pattern. If this is the case, then we've met the assumptions of normality, linearity, and homoscedasticity. Normality of residuals, linearity and homoscedasticity. So this is sort of what we're looking for. If you start to see any funneling or nonlinear trajectory that's occurring, like we've seen in previous lectures with examples, then that's an indication that homoscedasticity is not met or linearity is not met. And so we need to ensure the residual versus fitted is a plot you should always be looking at. So residuals are important. Hopefully that's emphasized it because the greater the assumption violation, the higher the risk of type 1 error, which is, it means more false positives. We'll talk about this more in future lectures. But fundamentally, with the standard error formula, which is used for confidence intervals and significance tests, they work when residuals are well behaved or normally distributed, right? So if the residuals don't meet assumptions, these formulas tend to underestimate coefficient standard errors, and they give you lower p-values and more type 1 errors. So you may be more inclined to think that your results are statistically significant when in fact it's a false positive that's occurring. And so it's really important to check that all your assumptions, but particularly your residuals, that they're normally distributed. So they're very, very important. And so these are the plots you're looking at, and these are sort of I've tried to give you sort of idyllic examples of what they should look like, so you have a good sense as to what a good standard is for meeting the assumptions there. So the key takeaways are that residuals are the difference between your predicted value and the observed values, the red line and your observed value. Multiple linear regression assumption is that residuals are normally distributed, and you want to examine residuals also helps assess linearity and homoscedasticity. So really, really important with our assumption checking. Great, let's get on to talking about interactions. So an interaction occurs when the relationship between an independent variable and a dependent variable depends on another variable. That's really, really critical, right? So the relationship between two variables, their relationship actually depends on another variable. Let me give you an example. Let's talk about drug interactions. You combine two drugs, you could get the effect of drug A and the effect of drug B. That's not an interaction effect. That's just an additive effect. So if drug A gives you more energy and drug B makes you more hungry, and then you take both drugs and you get more energy and more hungry, then it's just an additive effect. It's not an interaction. Or taking them together amplifies the effects of the drugs or dampens them. It gives a stronger or weaker effect than taking each drug separately. So it's an interaction. So you may, the reason why I use it here is it's commonly used in pharmacology, this term, which maps onto its statistical meaning. There may be an interaction effect where when you take the two drugs together, you get even more sleepy than if you were to take the sleepiness drug, even more physically active than if you were to take the physically active drug and the hungry drug together. So when there's an interaction, one drug affects how the other drug is expressed. So the effect can be multiplicative is the main takeaway, right? So in a standard regression model, there are additive effects. We're adding effects together, and that's what you see. In an interaction effect, where it's a multiplicative effect. When you multiply the effects together, you get something larger or even further dampened than you would typically expect to see. So an interaction occurs when the relationship between an independent variable and a dependent variable depends on another variable. I've said that again because it's really, really important. It's really the definition of an interaction term. So when we talk about interactions, we're talking about this concept, whether the relationship between these two variables depends on another variable. So let me give you an example from my own research. This one was looking at the relationship between age and brain volume and whether it depended on menopausal status. And I think this is a great example to show for explaining this concept, because it actually shows an interaction and no interaction side by side and what it means graphically. So let's start with an interaction here. So here we're looking at the relationship between age and total brain volume. And remember, an interaction is, does the relationship between your independent variable and your dependent variable depend on another variable, in this case, menopausal status? And so if you were to plot a line without menopausal status, you'll see, in fact, that the lines differ depending on whether the participants are premenopausal or postmenopausal. So in this example, it's is the difference between the lines equal, or do the difference between the lines differ as they go on? And in this case, you can see the difference between these lines differs as you go through the x-axis, as age increases. So in fact, yes, there is an interaction effect, and that's typically what you're seeing. So when you're looking for an interaction visually like this, you're looking at whether the lines are parallel, right? It doesn't matter where they are, but they're parallel, and the overall distance between them is all the same throughout as you progress, right? But an interaction is just when that difference differs, right, as you go across. So it could be like a complete opposite effect interaction, or you could get a slight slope, or like a deviation that you see here, right? So I'm not sure if any of that helped. Hopefully it did, but otherwise that's conceptually what it's all about, right? So the interaction is here. So for here, we can see there is a difference whereby whether if postmenopausal women had a steeper decrease in total brain volume than premenopausal women. Here, we're looking at, does the association between age and hippocampal volume depend on menopausal status? And actually, the lines are parallel, right? The difference between the lines is the same as you go through. So this indicates no interaction. So it does not depend on menopausal status for hippocampal volume here, right? Why is it adjusted? Is just because adjusted for head size. Everyone has different size heads, and that can influence the size of your brain. And so we adjust for that within the measure. But that's all that means, but it's practically the same meaning as what you're thinking about what the words mean. So that is what we see. Here on the left, we have our interaction. Here on the right, we have no interaction term, right? So that's an example of with the relationship between variable, the age and brain volume, does it depend on menopausal status or not? So interactions additivity is when independent variables act independently on a dependent variable. They do not interact. The effect of one independent variable on the dependent variable does not depend on any other independent variable. That is the worst sentence I've ever written. I'm very, very sorry. So, but it's very true, right? So the effect of one independent variable on the dependent variable does not depend on any of the other independent variables. Alternatively, there may be interaction effects. So for example, the magnitude of the effect of one independent variable on the dependent variable varies as a function of a second independent variable. That's the interaction, right? So the magnitude of the effect, for example, in that drug example, you get more hungry as a result of the presence of this other variable than with the variable alone, the drug provided alone. And so you may have heard the term moderation effect. It's the same. Moderation, interaction, exactly the same thing, or even words like synergistic that also or multiplicative. All of those terms relates to interaction. I know you're screaming, why is statistics like this? Yeah, I know, but it's the more familiar you can become with these terms, the better it'll be, and you'll connect them much better. So those are all examples of the words and terminology. So here's another example. Let's take university student satisfaction, which is independent variable 1, and the level of coping, which is independent variable 2. They might each protect against stress, right? So stress is our dependent variable. However, the independent variables might interact. So we can produce a multiplicative effect, right? We could see satisfaction by coping. Does it attenuate stress more so then either independent variable independently? For example, for those dissatisfied and not coping, maybe this exacerbates stress the most. So essentially what you should be thinking is, does the effect between the two, is it greater than the effects of them alone? Because that's conceptually what interaction is. It's saying the effects depend on something else, whereby the effects are greater with their presence together than individually alone as they are in additively. So here is it in the equation that should be familiar to you in terms of a regression equation, multiple linear regression. You have your dependent variable y, you have the variable 1, variable 2, and then here is 1, 2, which is your interaction, unique to an interaction equation where you have a multiplicative effect between 1 and 2. So B12 is the product of B1 and B2. And then B12 can be interpreted as the amount of change in the slope of the regression of y on B1 when B2 changes by 1 unit, right? So B12, the amount of change in the slope of the regression of y on B1 when B2 changes by 1 unit. So it's really looking at, if you think of those slopes again, it's as you increase in y, it's the amount of change in the slope of that regression on B1 as B2 changes by 1 unit, because it's a multiplicative effect. So here is another example of an interaction. So this one is, does the relationship between hormone replacement therapy use and brain health depend on ApoE genotype? So again, notice the structure of the question. When you see this word like depend, you know it's interaction. This is from my paper that was investigating this question. It was actually all around this concept of interaction. People had noted that in some cases there seemed to be effects in some studies, and others there weren't. And I wondered whether it actually all depended on this particular genotype, ApoE. So ApoE genotype, just very briefly, is a gene that we all have, and depending on the presence of certain alleles, you have E2, E3, E4. Depending on the presence of them, you may be at higher risk for dementia. So with every person, when you have a gene, you have 2 sets of alleles. And so you could have, for example, E3, E3, which most people have, but some people have one presence of the E4 allele, so E3, E4, or they may have E4, E4. And so those people with E4, E4 are at higher risk of developing dementia than those with E3, E3. And so my question was, perhaps the mixed evidence in regards to hormone replacement therapies use and brain health, maybe it was because of the effects of ApoE genotype, and maybe the relationship depended on whether someone had E4, E4 status or E3, E3 status and whatnot. So in other words, could the effect of hormone replacement therapy on brain health differ across genetic risk groups? So this can be tested using hierarchical regression. So for step 1, I looked at a brain health measure like cognitive function and neuroimaging measures, and hormone replacement therapy use and ApoE status, and a whole bunch of other covariates that we don't need to go into detail, but just keeping in mind that there's many things that impact brain health, and HRT use and ApoE status, and so they were controlled for, like age, sex, education. But for the purposes here, I've just put a simplified model. So brain health and HRT. So this is what we talk about in our typical regression thus far. Before we talked about interaction, this is our standard additive model. And then step 2 is answering the question that's asked up here, which does the relationship between hormone replacement therapy use and brain health depend on ApoE status, this multiplicative effect. And then you want to examine the change in R-squared to see whether the interaction term explains additional variance above and beyond the additive effects of hormone replacement therapy use and ApoE status. So what are the possible effects of HRT use and ApoE status on brain health? Well, it could be no effect. There could be nothing that we see in this study. It could be with HRT use only, there's an increase or decrease. ApoE status only, there's an increase or decrease in brain health outcome. It could be in the additive effect, they could both increase or both decrease. There could be a synergistic effect where it builds together to having a greater decline in brain function, or it could come together to have dampen the effects and have slower decline over time on brain function. So these were the results of the findings. So there was a 2-way interaction between hormone replacement therapy use and ApoE status. So 2-way just means that it's the 2 terms. And the reason why is because I actually also looked at a 3-way interaction here in this paper, looking at HRT, ApoE, and age, and looked at all 3. But that's why I've specified 2-way here. And the interaction effect was detected in the hippocampus, parahippocampus, and thalamus volumes. Specifically, women with the ApoE E4, E4 genotype who had used hormone replacement therapy showed 1.82% lower hippocampal, and then 2.4% lower parahippocampal and 1.24% lower thalamus volumes than women with the ApoE E3 genotype who had never used HRT. And so in this, this is just a small excerpt from a table, and I couldn't put the title in because the table is very large and this is halfway through it, but it shows you mainly the conceptually what maps on to here. So step 1, step 2. Here's model 1, right? And you can see I've just reported here the difference between those who used hormone replacement therapy and those who have not. And then here, it is all of the interaction terms compared to hormone replacement therapy use in E3 group. So that's why that's not reported. It's all relative to the E3 group. And you can see that those with the E4 genotype, they had lower, this is brain volume right here, and this is the confidence intervals. They had lower brain volume, hippocampal volume specifically, than the reference group here. And these differences in hippocampal volume, because again, it's more than just reporting the statistical significant effect, that's less than 0.05, but what is the size of the effect and is it clinically meaningful? And I found that, in fact, they're equivalent to approximately 1 to 2 years of hippocampal atrophy observed in typical health aging trajectories of midlife of about 1 to 1.4%. So this interaction was not detected from measures of cognition, interestingly. So we saw it in functional changes in the brain, but not in cognitive measures. So this suggested that the association between HRT use in specific brain regions depends on ApoE genotype. And so that's an example of an interaction term in real research being that's published, explaining how it's done through a hierarchical regression model and how to interpret the effect sizes there. And so one key thing to keep in mind when you're looking at interactions is when coming back to the concept of collinearity. So cross-product interaction terms may be highly correlated or collinear. In fact, more often than not, that you should expect they should be collinear. With the corresponding simple independent variables, it creates problems with assessing the relative importance of main effects and interaction effects. But what I want to state here is that, in fact, it's to be expected, right? If you're putting a model where you're having an example of the first variable, the second variable, and then a multiplicative effect of the first and second, they're likely going to have be highly correlated with one another. And so you're going to have multicollinearity. This is a context of emphasizing how we have guidelines in statistics, but there's also nuance in interpretation. And so when we talk about interaction effects, we're expecting there to be collinearity because we're looking at the interaction effect. So the key thing when you're running a model such as this is to note, is there an interaction effect or not, right? And so this is a case where collinearity is to be expected and is understood in the cases as to being there, and knowing that this produces a problem with assessing the relative importance of main effects because they have a lot of shared overlap in variance explained, but it still allows you to state whether or not there is a interaction present, and is less important when we talk about prediction of an outcome variable when it's included in the model. So the summary of interactions is in multiple linear regression, independent variables may interact to have no effect. They may increase the independent variable's effect on the dependent variable, or they may decrease the independent variable's effect on the dependent variables, right? So model interactions using hierarchical multiple linear regression. Step 1, you want to enter independent variables in. Step 2, enter the cross product of the independent variables. And then you examine the changes in R-squared to see what's occurring, and you also investigate whether the interaction is significant and meaningful as well when you're looking at the changes in the slope that's occurring. And that's everything. When we're looking at interactions, those are the key points. So keeping that in mind, the main takeaway is it's a multiplicative effect. We're looking at whether the relationship between two variables depends on another, and using hierarchical models can be a really useful way of looking at that. Okay, and saying that, grab another tea or coffee or beverage of your choice, or not, or maybe you want a hiatus from it all. We'll come back and we'll talk about analysis of change next. So I'll see you very shortly.